Hey everyone, this is the final video of asynchronous material for this week. So thank you for staying with me until this. So this one will cover inverse functions. So let me share my screen. Okay. Now, if we are given the function y is equal to f of x as 4x minus 3, then I've plotted out this function, which is the blue line, 4x minus 3. Now, how did we obtain different values of f of x? I plugged in a value of x and got different values of y. I plugged in a value of x and got a corresponding value of y. And I did this for a range of x values and I found out y values. And so that's how I got the graph. Now, is there a way to do the reverse? Can we go back? How do we get back x from a particular y? How do we do that? It's fairly straightforward. Now, the equation tells us y in terms of x, okay? Now, if I want to get x back from y, then I just have to rewrite the equation where x is written in terms of y. So how do I do that? So I have y is equal to 4x minus 3 is the original equation, the original function. Now I solve this for x in terms of y, and I find that x is 1 by 4y plus 3 by 4. And that I call that as the f inverse of y, or the inverse function of y. Because it's the inverse because I'm going back from y to x, and so the inverse function of y. Now, when we talk about inverse functions in general, when we're working with functions, we are working with the functions of the form y is equal to f of x. So if we want to find the inverse of that function, inverse of f of x, we have to follow these same steps, and we just have to do a couple more things. We have to flip the letters x and y. Okay. Now I'm just going to reverse. I'm just flipping the letters x and y here in this f inverse function. So now I'm going to get y is equal to 1 by 4x plus 3 by 4, and I'm calling that f inverse of x. Remember that we started off with f of x is 4x minus 3, and we have now found the inverse function of x, which is 1 by 4x plus 3 by 4. And how did we get here? Y is equal to f of x was our first one, and we wrote y as a function of x. That's how it's given to us. And then we wrote x as a function of y. And after we got that expression, we flipped the letters x and y, and then that's how we arrive at the inverse function, f inverse of x. Now, so we have two of these functions here. And how does the inverse function look? Let's plot it out. So I've written x values and I've filled in the f inverse of x values. Now let me go ahead and graph them on the line. So I have f of x given by the blue line, and I'm going to have a green colored line that plots my f inverse of x. Excuse me. And that's 1 by 4x plus 3 by 4. Now, if you notice, this particular point here is going to be 0, 3 by 4. Or is it 0, 3 by 4? Yes, it is. Okay, forget that point. I got carried away. Now, notice this point. This is minus 3, 0. The inverse function cuts the x-axis at minus 3, 0. And notice that the actual f of x function cuts the y-axis at 0, minus 3. Now, why I'm showing you this is because f of x and f inverse of x are mirror images about the line y is equal to x. So, when f of x is reflected on the other side of y is equal to x, the mirror image you get there is f inverse of x. And f inverse of x reflected on the other side of y is equal to x is your f of x. So what I'm essentially saying is inverse functions are symmetric about y is equal to x. That's an important property of inverse functions. Now, do inverse functions exist in all cases? Remember how we saw The definition of a function meant just like how we had defined a function, saying for every input there's only one output, right? Just like that, do we have a proper case where inverse functions they exist? Yes. So remember, inverse functions are, so if a function f of x helps you move from if it helps you move from x to f of x, then your inverse function is going to do the reverse. It's going to move from f of x to x. So what is the domain of f? What is the domain of f of x is now the range of f inverse of x, and what is the range of f of x is now the domain of f inverse of x. So this is all in other words. What I'm simply trying to tell you is that a function can have an inverse only if you can move from a single y to a single x. If you can move from a single f of x to a single x, then an inverse function exists. Or in other words, if you have a particular x value and an x can give you only one if you have f of x1 and there is only one input which gives you that particular output value, then the function is what we call a one-to-one function. One input maps to one output. And similarly, every single output has only one input. And when you have functions of that sort, those functions can have inverses. So a one-to-one function can have an inverse. Yes, inverse exists. Whereas on the other side, if you look at this graph here, for x1, you have the output g of x1. For x2, you have g of x2. So the same y value is generated by two different inputs. And this is still a valid function, but it's no longer a one-to-one function, it's a many-to-one function. Many inputs, not to one output. Now, can this have an inverse? Because it cannot. Because there are two, each output, there's one particular output which has more than one input. So for this particular case, a many-to-one function, an inverse cannot exist. Okay. And this is all this portion is just a very fancy way of describing inverse functions and technical way of doing it. Please do review that in the text. One important implication of inverse functions is that if you say have so this section here describes how if f is a single is a one-to-one function, then you can find an inverse g. And if g is the inverse of f is the inverse of g, because they're both going to be one-to-one functions, and you can invert one to find the other. Now, the implication of that is that when you take a composite function of this form, g of f of x, you're going to get back x. And if you do f of g of y, you're going to get back y. Essentially, when you have inverse functions, and if you have a composite function where the interior, one of the functions is the actual function and the other one is its inverse, the composite function, what is essentially happening is here the g will undo whatever f did to x and you end up with the input again. And f will undo whatever g did to y and you end up with y again. So that is the implication of inverse functions. Let's using this principle, let's see how the exponential and the log functions are very closely connected. Now, I'm just rewriting a few properties of the exponential and log functions. We saw in the last video how e power ln x is equal to x, and when e power u is x, u is given by ln x, and so on. Now, let me define two functions, where one is the exponential function e to the power a, and the other is the logarithmic function. Now, let me write f of g of x, which is f of ln of x. And when the input is ln of x, e to the power ln of x is nothing but x. So f of g of x is just given me x again, which means that f and g are inverses of each other. Let's try it the other way around. G of f of x is nothing but g of e to the power x. And now g of e to the power x is just ln e to the power x, which gives me x again. So g of f of x gives me x back, which means that g and f are inverses of each other. So e power x and ln x are inverses of each other, and this is a very important relationship to hold in mind. And you'll see this a lot in economic examples. So for right now, I'm just giving you indications or glimpses of where you'll see different concepts being used. Hopefully, when we cover more sophisticated mathematical concepts, we'll be able to dig into the deeper applications and illustrations of them in an economics context. Now, let me plot e power x here, and then I have y is equal to x middle line, and then I'm plotting ln of x here. Now, notice how e power x and ln of x are symmetric about the y is equal to x line. You see how e power x cuts the y-axis at 0 and 0, 1, and ln x will cut the x-axis at 1, 0. And there's just a lot of symmetry here. And at this particular point, say x is 2 and y is 2, you see how, or check these 2 points. When e power x is 1, e, you have ln x is e1, and this is going to be equidistant from x is equal to y1. And that's just the beauty, the graphical property of inverse functions, and the important result to take away and remember here is that exponential and ln functions are inverses of each other. And with that, I will be stopping the screen share for this video, and we are done with functions. And I'll see you next week in class, and we'll do some new topics. Have a nice weekend.